Hello, welcome back to the second course in physics. In this lecture and the lecture to come, we will be dealing with the electric circuits, and we will be concerned with the methods for circuit analysis. The contents of this lecture will include an introductory section. We will also come back to Kirchhoff's laws and its applications. We will see how we can apply these laws in a branch method, branch analysis, in a loop analysis method, in a node analysis method, the same laws but applied in different ways. And then we will discuss Millman's theorem in circuit analysis. We will also discuss how we can construct equivalent circuits, which is necessary and convenient for simplifying circuits for the purpose of the analysis. And in this sense, we will be discussing one of the important theorems, and hopefully, if we have time, to discuss this important theorem in circuit analysis, which is Kennelly's theorem. To begin with, we recall that we have mentioned Kirchhoff's laws previously, and we have discussed the elements of electrical circuits and the necessary definitions which are relevant to circuit analysis and the determination of the currents flowing in each branch of a circuit. Kirchhoff's laws, although applied to in the DC case, in the steady state DC case, direct current case, also can be generalized to the alternating current circuits, to circuits containing currents which are oscillating in time. But this, in this case, this generalization of Kirchhoff's laws would yield a system of simultaneous differential equations that can be easy to solve, but it can be also complicated, that we have to use advanced numerical methods for the solution of these equations. But anyhow, the solution of such equations is really important in the technological applications for electronic engineering. So if we recall that we have a generalized Kirchhoff's laws yielding these simultaneous differential equations, mathematical solutions, although these solutions could be abstract in a way, they are mathematical, more mathematical rather than looking like real physical or circuit analysis methods. But they are so important because these generalized methods for solving these equations would lead to the prediction of circuit behavior. And this would give us the possibility for circuit synthesis, for the synthesis of circuits with the desired behavior. And that led to the development of what we call the modular approach in electronic engineering, where circuits can be synthesized by simulation, and then we can, by knowing the behavior, what behavior do we want from a certain module, from a certain component of a circuit, we can produce that component, and we can put it on the shelf. And then we have components that are sitting there. Each component is known with a known behavior, and then we can construct any complicated device, including even mini computers, and microcomputers, we can construct such devices, such complicated devices, from off-the-shelf components, from the modules, what we call the modules. And that is arising from the general abstract methods of solving the generalized Kirchhoff's laws. And now let's go to discuss Kirchhoff's laws in a little more details and see how we can apply them to circuit analysis. Kirchhoff's laws can be applied in 3 different ways for circuit analysis, and these ways are generally in order to simplify the solution. We have the so-called branch analysis, where we set up a number of equations, simultaneous equations, that is equal to the number of branches. So we have a number of equations that is equal to the number of unknown currents flowing, each one flowing in a branch of the circuit. And the solution of these equations would give us the full solution for all the currents flowing in the branches. This approach is called the branch analysis. And the second approach is called the series analysis, or the loop analysis, or the mesh analysis. These 3 names go for the same thing, for the same method: series, loop, or mesh analysis. And we will use, for our purposes, the name loop analysis to identify this approach. And the third approach or method is the so-called the shunt approach, or the junction approach, or the node analysis approach. And these 3 names are given to the same method, but we will, for our purposes, we will use the name node analysis, which is the same as junction or shunt. We will call it node analysis. So let's have some examples to illustrate how can we apply Kirchhoff's laws to in these 3 approaches to apply it to circuit analysis. How can we use Kirchhoff's laws to analyze circuits? As we have mentioned before, for a circuit which has B branches, we have B unknown currents then to determine. And if we have n nodes in that circuit, then we have a total of B independent simultaneous equations. We need a total of B independent simultaneous equations in order to solve for the B unknown currents. And as we mentioned previously, from the n nodes, we can get n minus 1 equations by applying Kirchhoff's first law. And we can have B minus n plus 1 equations from applying Kirchhoff's second law. So the total number of equations that we have is B minus n plus 1 minus n plus n minus 1, and that gives a B equations that is relevant to the solution of B unknown currents flowing in the B branches. And let's take, for an example, this complicated looking circuit where we have 6 branches. The branch called A, that's 1. The branch called B, that is 2. The branch called C, that's 3. The branch called D, that's 4. The branch called E, that's 5. And the branch called F, that is 6. So we have 6 branches and 6 currents. And these currents, IA, IB, IC, ID, IE, IF, are unknown currents. And we need to apply Kirchhoff's laws in order to solve these 6 currents in the 6 branches. Now, the first approach is the branch analysis, where we have 3 equations from the first law. Why? Because we have 4 nodes. Node at V1, node at V2, node at V3, and the node at V4. These are 4 nodes. So n minus 1 is equal to 3. So we have 3 equations. The first equation is coming from from one of the nodes, for example, let's see, ID is here, and IC is here, and IB is here. So if we take this node at V1, at potential V1, this node, and apply Kirchhoff's first law, then we have the currents entering are equal to the currents leaving. So if we assume that the currents entering, when the current enters the node, it has a negative sign, and when the current leaves the node, it has a positive sign, then at this node, we will have ID with a plus sign because it's leaving the node, as we assume. IC plus IC, it has a positive sign because it's leaving the node, and minus IB because IB is entering into the node by assumption. And this summation of currents is equal to 0 according to Kirchhoff's first law. Of course, after we solve the whole thing, if we found that ID has a negative magnitude, for example, if it turns out to be minus 0.5 amperes, then we realize that ID is equal to 0.5, but in the opposite direction, in a direction opposite to our assumption. But we assume these directions for the time being. So this is from the first node. Now, from the second node, we have IB leaving the node plus IF leaving the node minus IA entering into the node is equal to 0. That's from the second node. And from the third node, we have IE leaving the node plus IA leaving the node minus IC entering the node is equal to 0. So these three equations are derived from from Kirchhoff's first law, and you can tell that we don't need actually the fourth node. We don't need it because if you add these three equations together, you will get the equation that you would get from the fourth node, which means that the equation from the fourth node is not an independent equation. It's just the summation of these equations. It can be derived from a linear combination of these already existing equations. So it's not an independent equation, and we don't need it. So this is all that we can get from the first law. Now, from the second law also gives B minus N plus 1. Now, B is 6, the number of branches. N is 4, so 6 minus 4 is 2, plus 1 is 3. So we must get three equations from the second law. And these three equations are, we can go through the loop. We can get IF times RF going from V2. IF times RF plus IA times RA minus IE times RE. We go through this loop here, and as we go through the loop, the summation of the voltage drops across the resistors is equal to the total of the electromotive forces along this loop, as Kirchhoff's second law mentions. So the electromotive forces across the loop as we go is equal to epsilon A, and it's in the plus sign because it is going with our direction. And on the other hand, the voltage drops across the resistors are simply IA RA plus IF RF minus IE RE, because here the voltage drop, we are going against the current. So we are opposing the current, so the sign is negative here. So this is from the first loop, from this loop. And from the second loop, we have if we go across the loop, we have the electromotive forces is simply epsilon D, and we go clockwise in this loop. So epsilon D we have on the right-hand side of the equation, for the summation of the electromotive forces across the loop. And now we go, this should equal to the voltage drops across the resistors. So we have here ID times RD, and we are going with the direction, minus IF times RF, plus IB times RB. That finishes the loop. So this is the second equation, IDRD plus IBRB minus IFRF is equal to epsilon D. That's coming from this second loop. And the third loop that we consider for Kirchhoff's analysis from Kirchhoff's second law is this loop. Again, we can take the counterclockwise in this situation. Counterclockwise, the electromotive forces in this loop are also epsilon D only, epsilon D, and it is positive because it's going with the direction. So epsilon D should equal to the voltage drops across these resistors. So it must be equal to IDRD, it's going with the direction, minus minus IERE, we are going against the current here in RE, and then minus ICRC, because again we are going against the current in RC. So we have the third equation, IDRD minus IERE minus ICRC is equal to epsilon D. So we have again three equations from Kirchhoff's second law. We have three equations from Kirchhoff's first law, and thus we have six equations that we can solve, and we can get the six unknown currents. The second approach is the loop analysis, and this loop analysis simplifies the analysis because instead of having the full number of equations, which is B, we reduce the number of equations and we only deal with the number of loops using only the second law, Kirchhoff's second law. So we are dealing only with M equations, which is simply equal to B minus N minus 1, or B minus N plus 1 equations. This is the number of loop equations coming from the second law. So this is obtained by eliminating the first law. And the way to eliminate first law is that we assume that in each one of the loops, we have a loop current. So we call the loop current I1 for the loop flowing in the first loop, and we assume that in the second loop we are having I2, current I2 flowing in the loop, and then we assume that in the third loop we have a loop current I3 flowing in that loop. So we have M loops and so on until we finish all the loops that are necessary from Kirchhoff's second law. And in order to illustrate these concepts here, we use only second law, and we assume the current I1. We don't deal with the branch currents now for the time being. We deal with the loop currents, and then knowing the relation between the branch currents and the loop currents, we can determine the branch currents if we know the loop currents. So first of all, in the first loop we have I1. In the second loop, we have I2. In the third loop, we have I3. We assume that these are the currents in the loops, and we use the second law of Kirchhoff, and we obtain three equations only in this case. Three equations with three currents unknown, which are the loop currents, I1, I2, I3. So this simplifies the problem dramatically. Instead of dealing with six currents, six equations, we are dealing only with three currents, three equations. So in this case, let's go through the loop one. We have I1 times, we go with the direction, the assumed direction of the loop current. So we have I1 is flowing in RA, I1 RA, and then we have in RF, we have two currents flowing, the current from the first loop and the current from the second loop. And those two currents are in opposite directions. So we have I1 as we go across the loop, I1 is flowing in the same direction, so plus I1, but I2 is flowing in the opposite direction. So the current flowing in RF is simply I1 minus I2. So I1 minus I2 times RF is the voltage drop across RF. And again, when we reach the resistor RE, again in RE, there are two currents flowing. The first current is I1, and it's in the positive direction because going in the same direction as we are going around the loop. And then we have I3 that's going in the negative direction, the opposite to our direction. So the voltage across RE is simply I1 minus I3 times RE. And this voltage drops across the resistors is equal to the total electromotive force around this loop, which is simply epsilon A. So this is the first equation from the loop analysis. And similarly, the second equation is coming from the second loop. So we have I2 minus I1 times RF, because here I2 is in the same direction as we go across the loop, the second loop. And I1 is in the opposite direction now as we go around this loop. Now, plus I2 times RB plus I2 minus I3 times RD, and that's equal to the total amount of the electromotive force, which is epsilon D in this loop. This is the second equation. And similarly, the third equation is I3 minus I1 times RE plus I3 minus I2 RD plus I3 times RC is equal to the total electromotive force, which is epsilon D, but in this case in the minus direction. So it's minus epsilon D because it's going against our direction as we go around the loop. So this is the third equation. So we have three equations, and we have three unknowns, which is I1, I2, I3. We solve the three equations, and we find the three loop currents. And we can determine the branch currents from the relation between the branch currents and the loop currents. So these relations are as follows. For example, IA in the loop, the branch current that is flowing in the branch A, IA, is equal to I1, because the only current flowing in this branch is simply the loop current I1 only. IB also is equal to I2, because the only current flowing in this branch is I2, loop current I2. And IC is equal to I3. However, in the branch D, for example, the current that is flowing is simply I2 minus I3. I2 down minus I3 up. So if this is positive, that means the branch current ID is flowing in the suggested direction. If this result is negative, I2 minus I3, that means ID is flowing in the opposite direction to what we suggested. And IE is simply I3 minus I1, I3 minus I1, and IF is equal to I1 minus I2. So from these relations, we have determined the I in each one of the branches. This is a demonstration of the loop analysis. And the node analysis, in this case, the first law is used to provide us with n-1 equations, and where we focus on the nodes or on the junctions at which we use Kirchhoff's first law, and we assume that the potentials at these nodes are unknown. So V1, V2, V3 are unknown, and V at the fourth or at the last junction, we assume that it is zero. The potential is zero as a reference. It's okay. We can set it as a zero as a reference potential. And now we can determine the current leaving each we assume that currents are leaving each junction, and we calculate the current leaving each junction, and the summation of the currents leaving each junction is set equal to zero. So let's go back to this example that we have we have considered before, we can set 1 over R as G, the conductance. It's just another way of writing the resistance. Instead of dealing with the resistance, we can deal with the conductance. The relation is G is equal to 1 over R for any of the resistors. So this is just to simplify the writing. So in this case, let's consider the junction number 1. The currents leaving the junction, we assume that currents are leaving junction number 1. So we have the current leaving in this direction along RD. The current is simply V1, that's the potential V1, plus epsilon D as we go across this, this branch. V1 plus epsilon D, and then we have a 0 potential, which is because this is V at this point is 0, it's grounded. So we have V plus epsilon D, that's the total potential, divided by RD or multiplied by GD. That's equal to the current across this branch. So this current plus the current across the second branch. The current across the second branch is determined from V1 minus V2. This is V1 minus V2. This is the potential difference across this resistor, divided by the resistor RB or multiplied by the conductance GB. That's equal to the current across this plus the current flowing in this branch, which is simply V1 minus V3 divided by the resistor RC or times GC. That's equal to 0. So the summation of all the currents leaving this branch is equal to 0. Leaving this junction is equal to 0. So this is the first junction or node equation. The second node equation is from the second node. So GF times V2 plus GB times V2 minus V1 plus GA, which is 1 over RA, GA into V2 minus epsilon A minus V3. And that is equal to 0. So this is from the second node. And finally, from the third node, we have GE, which is 1 over RE, times V3, V3 minus, minus 0, of course, plus GC minus V1 over RC, and then plus GA, oops, excuse me, I have to go back here, plus GA, which is 1 over RA, times V3 plus epsilon A minus V2, and that is equal to 0. This is, again, the summation of the currents leaving the junction 3. So now we have three currents leaving, we have 3 equations for the 3 node currents. And now we solve these 3 equations. We determine the potentials V1 and V2 and V3 by, if we determine the potentials, we can determine the branch currents from knowledge of what is the relation between these branch currents and the potentials and the determined potentials. So now, in mind that the potentials are determined, V1, V2, V3 are known because we have solved the 3 equations and we have known what are the potentials, then we can determine IA is equal to GA times V3 minus V2 plus epsilon A, and IB is equal to GB into V2 minus V1, and IC is equal to GC into V1 minus V3, ID is equal to GD into V1 plus epsilon D, IE is equal to GE times V3, and IF is equal to GF times V2. So this way, we have only 3 node equations. We solve for the 3 potentials and non-potentials, and from knowledge of the relation between these potentials and the currents in each branch, we can determine the 6 branch currents. And that is, this approach shows that we can use a lower number of equations to solve a lower number of unknowns, and then by knowing the relations, we can go ahead and solve the whole problem. So this approach provides us a simpler method. And now, as an example, we consider, for example, the double node circuit. This circuit is somehow simpler than the previous circuit. And we have two nodes, this one node at potential V, and this other node. We can set it as 0 volt. 0 volt just for reference, of course. And using the node analysis, it's simple to use the node analysis, because in this case, we will have only one equation to determine the one potential V, and from that we can determine all the currents that we need in all the branch currents, which are 3 branch currents. So the node analysis will give you, focus on this node, V minus epsilon 1, that's the total potential drop across this branch in terms of potentials, and that is divided by R1 or times G1, of course. That's the current across this branch. Now, plus V over R3 or times G3, that's the current through this branch, plus V minus epsilon 2 over R2 or times G2, that's equal to 0. This is the equation, one unknown, and we can solve it, and we can find the potential V. V is equal to R3 times, in parentheses, R2 epsilon 1 plus R1 epsilon 2, all divided by R1 R2 plus R2 R3 plus R1 R3. So this is the potential. This is an unknown potential, and we can solve for all the branch currents, because we know the relation between each branch current and between this unknown potential. Now this potential is known, that means the branch currents are known. This is just a demonstration of the application of this approach. And now we can move to use a theorem that can be useful for circuit analysis, and that's Millman theorem. And the Millman theorem is a direct method for calculation of the potential difference across a set of parallel branches. So if we have a set of parallel branches as this figure shows, we can calculate the potential across them. That means we can calculate VAB. And this is essentially important, like in the node analysis that we have just mentioned. So VAB, according to the theorem, is simply the summation of the electromotive force in a branch divided by the resistance in that branch. And this summation goes over all the branches, all divided by the summation of 1 over Rk, where Rk is the branch resistance. So this way we can find the potential difference between 2 points across a parallel set of branches. And to demonstrate, we can use the example that we have just mentioned a little while ago, and we consider the double node circuit, and we apply Millman's theorem, and we find that V, which is V minus 0, that's the potential between across this set of parallel branches, is equal to, here we have epsilon 1 over R1, and plus 0, we have epsilon here is 0 in this branch, plus epsilon 2 over R2, all over 1 over R1 plus 1 over R2 plus 1 over R3. These are the branch resistors. So this gives you the potential difference V across this set, and this gives you the potential at the node V is equal to R3 times R2 epsilon 1 plus R1 epsilon 2 over R1 R2 plus R1 R2 R3 plus R1 R3, which is exactly the same result that we just obtained from the node analysis by applying simply Kirchhoff's laws. This is just another way of obtaining this potential. And now we have to mention that in circuit analysis, it is very important to look for equivalent circuits. And due to the general form of Kirchhoff's laws, any network can be replaced by an equivalent network that we don't know the details of such a network, but we know how its behavior is. And the equivalent network must exactly simulate the actual network. This is the concept of equivalent circuits. And specifically, we introduce the following theorems in this sense that could help in the circuit analysis. And the first is Kennelly's theorem. The second is Thevenin's theorem. The third is the theorem of maximum power transfer. The next one is the Norton's theorem. And the last one is the superposition theorem. We can use these theorems for circuit analysis, and they can be very, very helpful in circuit analysis, as we will see. Now, in this lecture, we will mention only Kennelly's theorem. And Kennelly's theorem can be applied to the determination of equivalent resistors. For example, suppose that we have 3 resistors that are in the form of a triangle, or we call it the delta configuration. We have a delta configuration with the resistors. RAB is the resistance between point A and B. RBC is the resistor between points B and C, and RCA is the resistance between points A and C. This is the so-called delta approach or delta configuration. It is the same as this. It can be drawn in a different way, and this is called the pi configuration. Look notice that this is exactly the same circuit. It's exactly the same thing, but it's drawn in a different way. Now, according to Kennelly's theorem, this can be replaced by this circuit, where we can assume that we have a common point here in the middle, and point A is linked with the common point, and the resistance between A and this common point is RA. The resistance between point B and the common point is RB, and the resistance between point C and the common point is RC. And this is called the Y configuration of the equivalent circuit. And this can be drawn in a different way. It's just the same circuit, but drawn in a different way, which is the T configuration. They are the same. Now, according to Kennelly's theorem, the resistance RAB in the original circuit is related to the equivalent resistors as follows. RAB is equal to RA times RB plus RB times RC plus RA times RC over RC. Look, here we have RAB, and here we have 1 over RC. And on top we have these multiplications. And RBC is equal exactly the same thing as before on top, RA, RB, RB, RC, RA, RC, but divided by RA here. We have BC, RBC, and divided by 1 over RA. And similarly, RAC is equal to RARB, RBRC, RARC, same thing, but here we have 1 over RB. Notice we have RAC determined by dividing this summation by 1 over RB. This is the relation between the original resistors and the equivalent resistance. But if we need to determine the equivalent resistance from an original delta or pi configuration, the relation can be found, these resistors can be found by solving the previously given relations as follows. RA, the resistance that is between point A and the common point is simply RAB times RCA, look, point A as connected to the other 2 points, divided by the summation RAB plus RBC plus RCA. Notice that in the determination of all the resistance, RA or RB or RC, this sum will be exactly the same. But this is the only thing that varies from one calculation to the other. Notice also the connection that if we are calculating A, we have the resistors that are attached from A to the other 2 points, AB and AC. So, adopting this argument, RB is equal to RBC times RBA or RAB divided by this sum, RAB, RBC, RCA. This sum is simply the summation of all the original resistances in the delta configuration. And finally, RC, this resistance, is equal to RCA times RBC divided by the summation of the original resistances, RAB plus RBC plus RCA as before. At this point, I would like to finish this lecture, and we will be discussing the remaining theorems which are relevant to circuit analysis in the next lecture. And I thank you for your attention.